Okay, so in the past couple of days, we've looked at odd degree functions and even degree functions. And yesterday, we looked more in detail into cubic functions and quartic functions. And we looked at some general shapes of them. We looked at some of the characteristics of them. Now, today's goal is to basically generalize that and look at characteristics of polynomial functions in general. So before we get into the characteristics of them, let's go over some terminology that we need in order to best describe the functions and also talk about different parts of the graph. So the first term that we're going to talk about is the absolute or global maximum. Now what that means is the absolute highest point on the graph, on the function. So, for example, if you have a parabola that is opening downward, that vertex is the absolute highest point of the graph. So that is the absolute max. So is the maximum point of a function. It's the highest point. There is nothing higher than that. So if a function, for example, goes all the way to positive infinity, well, there is no absolute max because it's keep going. There is no highest point. Absolute or global minimum, on the other hand, is the lowest point of the function. So it's the minimum point of a function. It's absolute lowest point. Now, your graph might not have an absolute maximum or minimum, but it might have a local maximum or local minimum. Now, what does that mean? A local max is the highest point among the nearby points. So it's not the highest point of the function, but it's the highest point among the nearby points. For example, I'm just going to draw a little graph down here. So let's say I have this function here. You see that this function does not have any absolute maxes or mins. There is no highest point because it's going all the way to positive infinity and it's going all the way to negative infinity here. So there's no highest point. However, there are hills and valleys. So you have a point here and you have a point here. So this is a local max because this is the highest point among the nearby points. It's a hill. So wherever you see a hill, you have a local maximum. Local minimum, on the other hand, is the lowest point on the graph among the nearby points. So here, when you have a valley, so something like here, that's a local minimum. Okay? So take a moment to copy these down. Okay, something that's also, as I mentioned before, that's important to note is that a function might have a local max or minimum, but not having an absolute max or min. And you just saw an example of that I just drew. It had a local max, it had a local min, but it did not have an absolute max or min. Now let's get some examples. So here I have two graphs that I've taken them from a graphing calculator. That's why the quality is not that great. And because it's from the graphing calculator, it doesn't have those arrows at the end. So let's put that in to make sure that it's keep going unto infinity. Doesn't stop. So this is an odd degree function. So you can see it's going from quadrant 3 all the way to quadrant 1. It's odd degree with positive leading coefficient. And does it have an absolute max or min? No, because it's going to infinity. You're right, and going from negative infinity in quadrant 3. So, no absolute maxes or min. Oops. No, and O, and A. No absolute max or min. But does it have a local max or a local min? Yes. Wherever you see hills and valleys, that's where you have maxes and min. So here you have a local max, and here you have a local min. And you can just write the coordinates of it in your handout as well. Now let's get the next example. Is this even degree or odd degree? Correct. It's even degree with positive leading coefficient because it's going from quadrant 2 to quadrant 1. Again, let's put the arrows, both ends, going to infinity. Does it have any absolute maximums? No, because again, it is going to positive infinity here, it's going to positive infinity there, excuse me. So, no absolute maximum. Does it have an absolute minimum? Yes, it does. Because this point is the absolute lowest point on the whole graph. There is no point lower than this. It's not nowhere going to negative infinity. So this is absolute minimum. Okay. Now let's look at local maxes and mins. Does it have local max? Yes, there is a hill here. So that's a local max. And does it have a local min? Yes, there is a local min here. And that point that was an absolute min is also a local min because it is the lowest point in the nearby points as well. So it's both an absolute min and a local min. Okay, so everything okay about this? Let's now move on to actually talking about the key characteristics of odd degree functions, and then we're going to get to the even degree functions. So the first thing I'm going to talk about, and we've talked about all of these before, is just putting them under certain bullet points so we have it in front of us all the time. So the direction. By direction, I mean really the end behaviors. So where does the graph start, where does it end? Okay. So if you're talking about an odd degree function, the graph goes from quadrant 3 to quadrant 1. If it's a positive leading coefficient, and it goes from quadrant 2 to 4 if it's a negative leading coefficient. X-intercepts. So we are interested in knowing how many x-intercepts can you have when we have an odd degree function. So think about it. It's either from quadrant 3 to 1, which is again from below the x-axis to above the x-axis, or from quadrant 2 to 4, which is from above the x-axis to below the x-axis. Because your graph has to go from below the x-axis to the top of it, or vice versa, it has to cross the x-axis. So there is no way for an odd degree function not to have an x-intercept. It for sure has an x-intercept. But how many of them? It depends on the function. So it has at least one x-intercept to a maximum of n x-intercept, where n is the degree of the function. So if you have, for example, a cubic function, you will at least have one x-intercept. You might have two x-intercept, you might have three x-intercepts. Okay? So it's all depends on the function. Okay? Actually, you cannot have two x-intercept with a cubic function. You can have one x-intercept or three x-intercept, and we looked at why yesterday as well. So now maximum and minimums. We know that the graph of a cubic or any odd degree function goes from below the x-axis to above the x-axis, so it's going from negative infinity all the way to positive infinity. So there is no absolute maxes or mins. It has only local maxes and mins. So here when it says no max min, by that we mean absolute maxes and mins. So it only has local maxes and mins. Okay. Now the domain, we talked about it before. The domain of an odd degree function is all real numbers, same as the range. The range is also all real numbers. The last item we want to talk about is the symmetry. An odd degree function might have point symmetry. So we know that it's not going to have a line symmetry, but it might have point symmetry. Not necessarily it will, but it might have point symmetry. So I'll take a moment And make sure you have copied down this information, and then we will move on to even degree function. Okay, let's now talk about even degree functions. So first I'm going to talk about the stuff that are the same among all the even degree functions, which are domain, x-intercept, and symmetry. And then we're going to talk about positive leading coefficient and negative leading coefficient separately. So domain. Even degree function is a polynomial. We talked about all polynomials. There is no restriction on x, so the domain is all real numbers. X-intercepts, as we saw with quadratics back in grade 10 and grade 11, well, not all quadratics have an x-intercept, right? So with even degree functions, you're not necessarily going to have an x-intercept. But you might have up to the maximum of n x-intercepts, where n is the degree of your function. So you may have 0 x-intercepts, or up to the n, where n is the degree of your function. Symmetry. With even degree functions, you might have line symmetry. Again, not necessarily you will have symmetry, but if you do, it's going to be a line symmetry. It's not going to be a point symmetry. Now let's talk about positive leading coefficient and what's going to be specific about those graphs. The direction, essentially the end behavior. It's going to be, as we talked about before, from quadrant 2 to quadrant 1. Maxima and minima, it's a positive leading coefficient. So let's draw one that has a positive leading coefficient. So something like this. This is an even degree function with positive leading coefficient. So as you can see, it's not going to have any maximums because it's an absolute maximum, that is, because it's going all the way to positive infinity. But it will have absolute minimums, okay? And it will have local maxes and mins. Okay, so if it's a positive leading coefficient, it's not going to have absolute max, but it will have absolute minimum, and it might have local maxes and local mins. So have at least one minimum point. Okay? And by that, we mean absolute minimum. Whenever we just use the word minimum or maximum without local, that means absolute. And range of it, well, range is always from the minimum point all the way to positive infinity. Right? So all real numbers greater than or equal to the minimum of the function. Now let's talk about negative leading coefficient. So let's again draw one with negative leading coefficient. So something like this is negative leading coefficient. Direction goes from quadrant 3 to quadrant 4. Maxima and minima, again, it's not going to have a local min, but it will have, an absolute min, but it will have absolute max. So this one is an absolute maximum here. So it will have, again, at least one maximum point. And the range for it is all the real numbers less than or equal to your maximum point. Okay. So again, make sure you have all the information copied down. And we're gonna move on to the next topic, which is about finite differences. All right, so finite differences. Back in grade 10, and in grade 11 and even grade 9, you've done finite differences. You've done first differences, you've done second differences, and basically we did it for linears and quadratics. So we said that if the first differences were the same, the function was a linear function. If the second differences were the same, then it was quadratic. And then we stopped there. So if the second degree was the second differences were not the same, we just said it's neither quadratic nor linear. However, this year we're going to go further because we're learning about beyond quadratic. So we're going to learn about cubic, quartic, quintic, and all of that. So essentially, when you keep going and find the first differences. First differences, second differences, third differences, until you get that fixed value, the constant, right? So if you do it 3 times, you do up to third differences, then it's a cubic function. If you do it 4 times to fourth differences, then it's a quartic function. 5 times is quintic. Now, you can use this expression here, which is A, where A is your leading coefficient. I'm just going to show this. And N is the degree of the function. And you're just multiplying N by 1 subtracted from it, by 2 subtracted from it. You keep multiplying until you get to 1. So if it's, for example, N is 5, it would be 5 times 4 times 3 times 2 times 1. For those of you who are familiar with it, especially if you've taken data management, this is called N factorial. Okay? So A times N factorial is equal to the value of your finite difference. Okay? So you keep doing your finite differences. Let's say you did it 3 times, so you realize it's cubic. So then your N is the degree of the function, which is cubic, so this would be 3. So it would be 3 factorial. So A times 3 factorial is equal to the value of that difference. So if we found out that constant is -2, you set that equal to -2. And then you can solve this equation to find the value of leading coefficient. So essentially, from a table of values, using this equation and some other information, you can actually go back and construct the equation of the function and get what the equation of the function is. Okay? So you might be a bit confused right now, but let's take a look at an example. Okay? So in this example, we want to use finite differences to determine first the degree of the polynomial, the sign of the leading coefficient, and the sign is the same sign as the value of the constant at the finite differences, and the value of that leading coefficient. Okay? So go ahead and try to do at least the differences part, and then we're gonna continue with the rest. Okay, so when we look at this, we'll see that I did the first difference, and first differences were different. I showed that with blue. In green, I did the second differences. They were still different, so I continued the third differences, and finally in third differences, which I showed with red, I see that I got the constant, which is 6. So this means that N equals to 3. So I have a third degree polynomial. So that's the answer for the first part. The degree of this polynomial is third degree. It's a cubic. The sign of the leading coefficient, so the answer to this one, the sign would be positive because the number that I got is a positive 6. So it's going to be positive. And now it's asked us for the value of the leading coefficient. So we said that the value of the leading coefficient is that an factorial equals to the constant that I got. Constant that I got is 6, so it's equal to 6. My n is 3, so a times 3 factorial equals to 6. Now 3 factorial is 3 times 2 times 1, which is 6. So a times 6 is equal to 6. Therefore, a is equal to 6 divided by 6, which is 1. So my leading coefficient is 1. Now, take the time, do the next example yourself, do the whole thing yourself, and then check the video. I have the answers for you. So pause. Okay, so this is the solution for the next example. It has, until we reach the constant, we have to do 4 differences. So it's a 4th degree function. The sign is negative because the constant that we got is a negative value. Then to find the value of the leading coefficient, we use the formula an factorial equal to -24. N is 4, so it's 4 factorial times a is -24. 4 factorial is 4 times 3 times 2 times 1, which is 24. So 24a is -24, so a equals to -1. Okay. So tomorrow in class, we're gonna summarize it and do more examples and practices involving this and see how the general look of the functions will affect them. All right, have a good day.